Hi, everyone, and thank you for joining Lattice today here at our LinkedIn Live. My name is Matt DeBroge, and I'm representing our marketing team here at Lattice. And I'm super excited to talk about AI today. But specifically, we're going to talk about accelerating artificial intelligence at the edge. And today, to really talk about this in a much more detailed way and a really meaningful way, we have two really special guests. So first, I'd like to introduce Bob O'Donnell from Technalysis. Bob, maybe tell us a little bit about yourself.
Sure. Thanks, Matt. So again, Bob O'Donnell, Technalysis Research. I've been a tech industry analyst for just over 25 years now, working with all the biggest household names in tech, from the semiconductor players and suppliers up through devices and software and systems and carriers and cloud providers. And of course, these days, everybody and their brother's talking about Gen AI. And I've done several research reports recently on Gen AI. So really looking at how it's impacting all the way across the supply chain, use cases and everything else. So super excited to be here today to talk about this, because I think this is a really interesting area, this notion of bringing AI down to the edge.
Awesome. Bob, thanks for joining us today. And Mark, maybe you could just tell us a little about yourself.
Yeah, so Mark Hoops, Lattice Semiconductor. I manage our industrial and automotive segments. Been here a little over 4 years. And our big focus at Lattice is industrial automation, autonomous machines, and been working on that for quite a while. So we've got a lot of great solutions and things to talk about today on where we play in those areas.
Awesome. Mark, thank you for joining. Bob, thanks. Let's dive in. All right, so AI is definitely a major growth factor for the entire semiconductor market. We are seeing, definitely revenue growth in this category from our business. We are seeing a major refresh cycle happening in the data center, driven by partners like NVIDIA. But as these AI capabilities are getting down to the edge, and everyone is trying to access the compute and the capabilities of that compute with AI across every possible application, we're seeing a lot of developers leveraging FPGA technology to solve a lot of these challenges. And the reason for that is because of really the flexibility, the low power capabilities of our FPGAs, and some of the unique security and privacy capabilities that our FPGA offers that really make our Lattice FPGAs a great solution for these edge applications. So we want to talk a little bit about that in more detail. And to start the conversation, I wanted to, Bob, would it be okay if you maybe gave us a little bit of the landscape across all the different edge AI solutions and what you're seeing, and what are some of the trends that are ultimately our listeners should kind of know about first.
Sure, Matt. Thanks. Like we said, everybody's talking about AI. And initially, of course, all this started with ChatGPT, right? We saw this tool that you could go online and you could, put in these requests in and ask for summarizations and all this kind of crazy stuff. And we're like, wow, this is incredible. And we started thinking about Gen AI as this thing that's being powered by these huge clusters of NVIDIA GPUs and doing all this incredible stuff. But what we've seen happen now is the idea to take these AI models and then bring them down to other devices. So now we're seeing AI happen, on client devices like PCs and smartphones. And we're also seeing AI being developed and being able to run on the edge. And that could be for industrial equipment. It could be for medical devices. It could be in automotive. It could be in robotics, all of these things. Because what we're also seeing is the creation of new types of less power demanding hardware, right? I mean, you can do the big GPUs and then you can do the smaller GPUs and still run these applications. And we've moved from large language models, which of course are very important for these big cloud-based services. Now we've got small language models and other smaller models that can run in these more compact devices. And so all of a sudden we're seeing Gen AI move from just being this cloud-based thing into all kinds of other interesting areas. And that's why this is so cool is we're seeing this technology really start to be deployed in a lot of places that initially I think people hadn't really thought about.
Got it. So basically all of the things that we can imagine that these trained AI models are doing in the data center, they're going to be doing at the edge, but maybe in a little smaller or more specialized type of data set. Is that the way to think about it?
Exactly. I mean, they're being adapted to these new environments. The models are being adapted. They're being focused to very specific applications, and yet sort of the magic of what they're able to do the data analysis, in a way that, remember the days of big data, we'd say, hey, if we get all this data, we're going to do this data analysis, and big data is going to solve everything. And at the end of the day, it didn't really do it. But now Gen AI is kind of delivering on that promise, and we're able to do data analysis and image recognition and all these kinds of things in a really intelligent, meaningful way. And it's all of a sudden, it's the idea that, wow, all of a sudden there are these things that we kind of dreamed about, we thought we could do, that we actually can, and here's the way to do it. But there are steps along the way, there are hardware elements along the way, and there's the big things we know about, like the GPUs, but there are a lot of other pieces that need to interconnect to make all of this really work together.
Wow, thanks for that, Bob. That's very insightful. And Mark, like, as I think about this, right? So okay, we got this capability that's making its way down to the edge, right? When I think about the edge, there's sensors everywhere to try to determine everything from whether a product in a factory is good or bad, whether a autonomous robot has to go to the left or to the right. There's sensors everywhere. So are these sensors going to like just connect to these SoCs with this capability for these large language models at a smaller size, or like how should we think about like the actual deployment of this at the edge the way Bob described it?
Yeah, sure. So the two things. One is the trend basically towards automating as much as possible, making factories run autonomously. So that requires robotics and advanced kind of designs that require many more sensors, higher resolution, low latency. All these things need to be able to run real time. And they want to be able to run that so that they can reduce, say, the human workload or reliance on humans in a factory, but not eliminate them. So they need to work with humans and be safe around them. So they need to be able to react in real time. So with that, you need more sensors, you need low latency. And the devices that are out there are very, very good for edge compute in terms of doing AI and things like that. But they're limited in how they can connect up to things, especially if the sensors, you have a multitude of sensors, you have higher resolution, you need to aggregate them because you're limited in the number of IOs you have in the main compute platform, which would be like an Intel PC or an NVIDIA Orin based edge platform, as an example. So the roles FPGAs play is to help to bridge and aggregate all those different types of sensors and stream them seamlessly into the compute engine that can help run some AI. In addition, we can pre-process and do things like sensor fusion in real time, do real-time motor control, safety functions, and even do some very, very low power hybrid processing where some AI will be done in the FPGA and some will be done in the compute engine. So those are all the benefits that we can bring into systems at the edge that are demand real-time kind of performance and low power and predictable latency.
Mark, so that just to kind of just to double click on that a bit. So what you're saying is that the SoCs have tons of compute capability, right? And they can essentially, that compute capability can be at the edge, but the actual connection to the sensors is something that is not native to that SoC capability. Bob, like, is there like or can you maybe just describe like the overall industry trend in the SoCs and the compute investments and how that relates to just some of the kind of the peripherals and some of the systems that are out there and some of the applications like Mark's talking about that require different latency timing loops and determinism that, how do those two different trends kind of play out in your mind?
Yeah, I mean, because one of the interesting things, Matt, is when we think about what NVIDIA is doing with GPUs, what's happening with CPUs, we're talking about moving to process nodes of 3 nanometers and 2 nanometers and all these incredible things to enable the level of processing that's required to run these algorithms. The practical problem that you run into is that the sensors are not being manufactured at that level. And so if they're at 20 nanometers or 28 nanometers or even higher, you can't add this big fat pipe, to try and connect onto the SoC. You need some mechanism that enables you to interface between, this super low process or these low process nodes to the wider connections, and you have to do it in a way where the timing is consistent. And I know Matt can talk more about some of the details of software versus hardware, but at the end of the day, it's just that practical need, like, hey, I got to figure out a way to get data from here, in these kinds of devices with this kind of process node down into this one. And they can't add that to the SoC because it would drag down the other capabilities. So you have to have this middle, interface kind of chip. And that's the role that FPGAs can play in this.
Got it. Okay. So essentially the journey to lower process geometries or smaller process geometries across compute is enabling unbelievable new applications around AI. But to actually be able to use those applications with the sensor environment that's out there at the intelligent edge, you have to be able to then fan out those IOs to be able to drive that connection across all of those different, AI use cases. So thank you. That's really, really insightful. So Mark, I got to ask now. So what are customers doing to solve these problems? Not just from our perspective, but if you are in a smart factory setting and you're trying to design the next, autonomous automotive or, smart retail scenario, what are you doing right now? What are your options and how are you solving these kinds of problems?
Oh, yeah, sure. So first of all, in industrial automation, people have been modifying Ethernet, which is not real time, to make it real time for a long, long time. And you've got more than a half dozen different standards there. But bridging things over Ethernet, which is ubiquitous, high performance, low cost, is great. What you need to do is make sure you have the timing and predictability and bandwidth that you can get in there. So traditional industrial networks are down at 100 megabit or gigabit. That's too low to bring in massive amounts of sensor data, like from cameras and things like that. So if you bump it up to higher speeds, like 10 gig or 25 gig, you can bring in more sensors and bring in the raw data for processing at the central node. So that's what FPGAs have been starting to do now. And there's a solution that we have with NVIDIA that enables you to connect up to various different cameras, radars, LiDARs, bridge them into or analog sensors and bridge them into the FPGA, which then seamlessly streams that data in a pipe into NVIDIA Orin platform, as an example. And then the software model for connecting to and updating drivers and things like that is also much more simplified, because you don't have to deal with all these separate complex protocols of the native sensor interface. You're just dealing with things that are Ethernet packets of data.
That is a lot to unpack there. So I'm gonna take a step back there. So what you're saying is that Ethernet is becoming more and more important to solving some of the video interface complexity challenges because of the open standards and the kind of ubiquitous expectations for what that video pipeline can look like downstream, right? So what you're saying is we're actually leveraging Ethernet in partnership with NVIDIA to try to standardize some of those things. Can maybe you can just kind of tee up what are the kind of use cases that solution enables, and maybe Bob, what are some of the use cases, and maybe you guys can decide who goes first on them. What are some of the use cases where if you enable all these things together, what kind of things can you create for end customers in the marketplace? That's kind of the next question I have for you too.
Yeah, I mean, Matt, go ahead. You can go first, and I'll offer some thoughts as well.
Yeah, sure. So first of all, systems have to be scalable. So in terms of, you need to have small systems where maybe you have tiny cameras have to get in little places to be able to do inspection or manage control of a system as you're producing a function. Or you may need to have larger, more extensive, further away type sensors in the overall system. Maybe you got an assembly line running and you need to be able to look at various different stages of it and control the whole process of the quality of the machine or something like that. So you need a lot of flexibility in terms of where your sensors need to go, long distance, short distance, how big or small they need to be. And so the ultimate kind of flexibility you get from that is through Ethernet. You could also do in some cases wireless, but wired is more predictable in terms of no interference from any kind of things such as that. So it gives you a ubiquitous way to scale the system, and then the FPGAs at the edge can bridge it to the native interface, whether it's MIPI or LVDS or JESD or whatever the interface may be. It doesn't really matter. And we handle all the control signals, bridging all that kind of things. to translate control of the sensor and streaming the data into the compute platform to make it easier for the end vendors to implement very flexible, complex systems for production or transport, shipping and receiving, any of that kind of stuff, whatever type of factory it might be.
And it's interesting when Mark and I were chatting beforehand as well. One of the interesting things he brought up when you think about some of these applications like manufacturing, where their timing, it's measured not in milliseconds, but in microseconds and nanoseconds. And a lot of times in the past, there have been software loops to kind of deal with the interface issues, but that doesn't work in these environments. If you need it really precise timing, that's another beauty of the FPGA, because it's just running bing, 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 bing always, and so you can be consistent in the manner with which it feeds data into the GPU or what other element you need. So that's going to give you a more consistent experience, a better experience, and obviously it's going to make sure that operations run the way they're supposed to. And so applying that to real world applications, if you've got robotics, if you've got industrial machines, if you've got medical information or what have you, all of those things, a lot of that's got to be very precise in terms of the timing. And another thing that I think is important to mention, and I think I forgot to mention this in that earlier discussion on AI and moving to the edge, is there are a lot of these applications, and medical in particular is what made me remember this, with the HIPAA laws that exist where your personal medical information can't be, put out anywhere. That's one of the reasons why we're seeing the creation of, these compute platforms like Orin and what have you that will run on a local device with local data, not have to go to the cloud, because you avoid the potential security and privacy risks that happen if you have, private medical information going out to the cloud. So yet another reason why you need to see these compute devices and then those interfaces directly on the device. So it becomes a system of its own, so that's the other thing to remember, because again, we get so caught up with the big NVIDIA GPUs in the cloud, but hey, there are smaller NVIDIA GPUs and SoCs that combine ARM cores and the NVIDIA GPU cores, and all of that needs to function locally. So, and with the precise timing, obviously the other benefit of doing it locally is, you can avoid any round trips to the cloud, which would certainly not work in a number of industrial environments. So it's that combination of being there precisely, providing that consistent clock. And then, as you said, Mark, tying it in with, there are standards to get Ethernet to be timed, where there's, real-time signaling available with certain variations of Ethernet. So bringing all those elements together is what makes it possible, because you get that consistency, you get the bridging. And so it becomes the FPGA becomes that absolutely essential link between the sensors and the data they create, and then the compute devices that are doing the work.
No, that's fantastic, Bob. Thanks. That's really great insights. And so, like, super clear on the latency, security, and the privacy use cases that you both described. Talk to me about the flexibility that our developers are looking for. We clearly have a great partnership with NVIDIA and that platform, and I actually want to learn more about that. So I'm going to kind of tee you up to tell us more there. But like, how many solutions are there? Is it like, is it pretty consolidated? Is it like one kind of solution is kind of driving, one type of design, or is it very fragmented? Mark, maybe you could just talk a little bit about, what you're seeing in terms of like, how many options are there out there?
Well, I mean, in terms of fragmented, if you just look at the classic industrial Ethernet, like I said, there's a half dozen different standards plus, right? And that's not even including things like TSN, stuff like that. So then there are lots of sensor interfaces, and they're changing the bandwidth, the latency, all of the interfaces over time are changing. So you need to have adaptability in the system, basically, to be able to accommodate all the different changing things at the same time. And that's what the FPGAs bring, is being able to adapt. And another thing too is being able to improve overall, besides the flexibility, improving speed of operation and flexibility and adaptability. So just think about it. The faster you can put something through in a factory, the more money you make. The factory has to stay up, so you need to make sure it's got predictive maintenance and analytics to understand that none of these machines are degrading and going to fail in the system. But the higher speed you can run a conveyor belt, or the faster you can run a robot, the higher your throughput is and the more money you make, right? So it's uptime and throughput. And to do the throughput, you have to have real-time, very fast loop cycles. And that's where the hardware comes in and helps out in terms of processing. It's reducing the latency, increasing the performance. And you're going from dumb machines like initial robots could not work with humans. You have to basically isolate the humans because they're not safe. And they weren't very flexible because they have to follow a certain line or look for a certain pattern. They're relatively stupid, but they can move things for free, almost, just battery power. Now they're going from that to, I can go anywhere, I can go faster, I can be safe around humans. So it gives you much more flexibility and adaptability to respond to market conditions and production needs in the factories.
You know, those dumb robots sound a lot smarter than my teenager. but I hear you. We're in the early innings, I think, is your point. You know, and flexibility, the way you just described it, with all the different implementations and variables and knobs you have to turn, it's pretty clear. Can you talk a little bit more about the NVIDIA platform, and then maybe talk about how end customers can leverage this, and then overall, I'd really like to get also a sense of if there are places where our developers should really focus on, given some of the market trends in some of these applications. Bob, I'd love to hear where you're seeing the biggest investments, and places where we can potentially increase some of the things that Lattice is doing to make sure that we're driving the right impact in the marketplace.
Yeah, sure, Matt. I mean, look, we've been talking about a number of these areas that are clearly looking at this stuff. So medical is a big area, medical devices and equipment, robotics, and by the way, everybody tends to think of the humanoid robotics, but there's a lot of robots that are just these little, devices that essentially lift up a skid of stuff and move it around, right? I mean, these are not necessarily the humanoid robots that we all tend to think of when we hear that. And so all of those kinds of devices are being deployed in factories. It's a big deal. We're seeing a lot more, obviously, robotic manufacturing, and the safety point that Mark brought up, I think, is really critical to remember too, because that's a huge factor, right? If you're going to have these devices starting to do things, you're going to want to have people around, and you got to be sure that, of course, they can be safe. And that's one of the benefits of we're seeing with Gen AI. We're moving from these dumb robots that really were very limited in what they could do to robots that, let's not say they're thinking, but they certainly act in a much more intelligent manner, and they're much more aware of their surroundings. Again, thanks to higher quality sensors, more processing of that sensor data, so they can be cognizant of the surroundings that they're in, and react accordingly. So, again, I think robotics is going to be a big deal in lots of different forms. I think medical devices, industrial manufacturing. Eventually, I think we'll see, obviously, automotive is doing their own kind of versions of some of this stuff. But for now, I think it's those main industrial applications, and it's process automation too. I think that's important. I just did some research on how companies are using Gen AI. And by the way, almost 80% of the companies that I surveyed said they were going to do some level of AI at the edge. So 100% of these companies that I surveyed are already doing AI for enterprise applications, but almost 80% said they would also be doing it at the edge. So that's a huge market opportunity out there. And when you look at some of the applications, they said, process automation is part of what they want to be able to do. And there's a lot of ways to interpret that phrase of process automation. But all of those things, I think, become important. And again, that notion of running it locally, for privacy purposes, for security purposes, and, oh, by the way, for, just moving it off the cloud. We can't have all these GPUs running in the cloud. We'll never have enough power. So there's real practical needs to run some of these models on device, whether it be client devices or edge computing devices. And eventually, I think we'll even see cost reductions, because, hey, if I'm doing the compute, why should I pay OpenAI? Because I'm not using their infrastructure. I can pay less. I can use their models, but not necessarily their physical infrastructure. So all of these things, I think, come into play, and that's what's driving a lot of the excitement in this area. So anyway, long answer to a short question, but I do think we'll see a number of different implementations of as I said, industrial manufacturing of robotics and medical devices for sure to get started.
No, that's fantastic. That's fantastic. So I'm going to press Mark again to
Yep.
tell me a little bit more about the NVIDIA partnership. When you talked about moving the data or moving the processing from the cloud to the edge, the power thing immediately went off in my mind, right? Like data center power, like all the house lights dim to turn on your AI data center, right? So I'm just that visual came up to my mind, right? So I feel like power is also super important, and I know that we are focused on making sure that we can enable all these use cases in a low power way. Mark, maybe talk a little bit about, a little bit more detail about the NVIDIA collaboration and how this is also helping deliver, really low power, use cases, and not just the, higher power use cases that everyone's kind of focused on right now with Gen AI in the data center.
Sure. Yeah. So, Orin is developed for the edge. So the Orin Jetson platform is developed for the edge. It's power optimized. It has, I think, 10, 20, 30, 50 watt kind of power, depending on the amount of compute power you have. And the solution we've done with NVIDIA is the compute engine. And the pipe that feeds all of the data into it is single or dual 10 gigabit Ethernet links. And there's a software stack that makes it very easy to configure the sensors that are connected up and to stream the data automatically into the proper locations within the NVIDIA platform to do the compute on it. And the FPGAs, the Lattice FPGAs, play a role where we have what's called a sensor bridge board. And it has a Crosslink NX to connect up to cameras or MIPI-based interfaces, and a Certus Pro NX to do the packetization and connect up to, say, A to D sensors with JESD and other types of interfaces. And all of the packetization and all of the prepping and streaming of the data comes through the Lattice devices, streaming into the Orin platform where the compute engine happens. But in addition to, we're not just limited to stream the data in. We can do edge processing and pre-processing and send in information as well. We've had some vendors reach out to us saying they're getting a little bit concerned about all the things they need to do in this compute platform when they have to do them in real time and they have to add this sensor and that sensor. Software guys are getting a little bit concerned about all the things they have to do. So they're asking us, hey, can you do some of that LiDAR processing? Or can you do a little bit of, sensor fusion processing? And how can you help me out so I don't have as much to do in the central compute platform? And that's another thing FPGAs are pretty good for, because those types of sensors require parallel processing, and the FPGA architecture is perfect for doing the parallel processing of the information and time aligning it precisely from between different sensors, so you can synchronize things and cross-correlate data from different sensors. So lots of different ways we can help out there. We have a sensor fusion processing demo that we put together. That's processing LiDAR, camera, and radar, and it does all that simultaneously for under 1 watt. So it's pretty impressive in terms of the power you can get out of it.
That's pretty fantastic.
That's pretty cool. Yeah. I got to admit, even, as a third party, I'm like, damn, that's pretty cool. That's the ability to do that, and what it says to me is, I think, reflective of another trend that I've said. Sorry, Matt, to jump in just for a second, but this notion of distributed computing, I think, is really going to be a big deal over time, right? Because the idea that everything has to be computed in one place just seems increasingly not realistic for a lot of different reasons. So as systems get smarter and as software gets smarter, that idea of being able to pre-process certain things, in the FPGA before you hand it off and clean up the data, probably more than likely as well, it just makes sense to think about sort of that system level approach to architecture. And you're hearing more and more companies talk about this idea of a sort of a systems architecture. So I think it's really cool the way that all these pieces work together.
Little gears in front of big gears type of thing.
There you go.
Oh, that's wonderful. No, that's fantastic. So Mark, if you're a developer, if you're a end customer, banging your head against the wall, trying to figure out how to fit, all this compute capacity, into the arm of a robot, how do they find out more? How do they reach out to you? Do they reach out to you on LinkedIn? Do they show up at your front door? How do they get more information from that really great feedback you're giving us? And
yeah, so we'll put a web link into the thing that people can click on and go to a web page that has more information on our sensor streaming platform with NVIDIA, and then there's a way to contact us through that webpage. So that's one of the best places probably.
Oh, that's fantastic. I appreciate that, Mark. Bob, I really appreciate all the industry insights. AI is certainly a growth driver for our business as much as every other company out there at the moment. So really appreciate all of your feedback and time today. Really thoughtful and insightful commentary as well. So very much thank you for that. I do want to let everybody know that we do have a much larger developers conference for Lattice coming at the end of the year. We actually have it scheduled for December 10th. And you can join us on our LinkedIn, our Facebook, our Twitter, and learn more. And we will also post that link for our Lattice Developers Conference on this post as well. So I just want to thank everybody for listening. There's a huge opportunity around artificial intelligence, but it's not just in the data center. It's at the edge. It's requiring a lot of flexibility. FPGAs are great to solve these current system challenges. And we have a lot of great partners and insights on how to help. So really appreciate your time today. Thanks you again for our panel, and looking forward to seeing you all at the Lattice Developers Conference on December 10th. Thanks again.